Okay. Rearranged. Okay. So we have a chapter 1. The topics you might put under review. Okay. So we won't have a calculus yet. Going back and looking at some things that you've seen before. Usually several times. Now, because of the several times, we're going to look at some of those things a little differently. We're only going to worry about the things that at this point we really need. In math, there are things that you study, you work on, which gives you the next thing, right? So we don't need to go back and have all those little things again. So that's part of what will be a little different looking at that. Other things, at this point, maybe we can take a little different look at the same thing. Because you know things now. But the topics, well, I hope, all you've seen the words before and you have some inkling we did something like that. So. Okay, now, as we progress, there are things that we look at. So we do the what? Why is this? What is it? Explain, right? So that's part of what we do. So, and then you do problems around that topic, right? So sometimes we don't have problems which are directly in the why or the explain, but it gets us started. This is why we're doing it. This is what it is. This is a way to think about it, those types of things. So within class, I'm going to try to make that a short part, and then you can look more closely at the videos or the book to fill in maybe more of that side. So I'll give you enough of that, and then together we'll try to look at some of the problems related to it. So that's the idea. And I'll try to tell you when I'm doing what. It gets a little confusing if I start doing the why and explain and then throw in problems and you don't know I switched. Right? So, the first section, the topic, exponents. You probably know something about exponents, right? Probably know basically what they are. So if I wrote 2 to the 4th, you know what that means? What basic number is that equivalent to? Yeah. Because it means 2 times 2 times 2 times 2, doesn't it? So I think not too much, you remember that much, right? Some of you more, some. But what are we doing here? We have this figure, which is, in total, is said to be a power. In this case, the fourth power of 2. Within the same notation, there's this thing, the superscript, which is the exponent. And this number, which is known as the base of the power. So you kind of remember that, but you might have forgot those words a little. Now, when I write this as 2 to the 4th instead of 4 2's, oh, number. The exponent tells you what? The number of factors. So it counts the factors, doesn't it? And so I bring this up because you can look at working with exponents in that way. The exponent is always telling you how many factors. And the particular base, whatever symbol I happen to use, won't make any difference. X to the 4th means 4 factors of x, doesn't it? And instead of running through, here are the basic rules of exponents. Let's see if you had the exponent and all those. We could look at them in basic form that if we took these two powers, x to the 4th and x squared, the result is still a bunch of x factors, isn't it? And it just says we get 4 factors followed by 2 more. This counts the factors, so up here in the exponent, it becomes a sum, doesn't it? It's part of the history of, we'll get to it later, logarithms and the relationship of the exponent to this is the fact that, oh, the powers down here, we multiply. The exponent, it becomes the simpler operation of addition, doesn't it? But the rule makes sense if you think it's just counting how many factors. You can also make sense out of counting backwards. So how many factors? Well, we would have 4. Now we have to go backwards 2, right? So get rid of that one, and we've backed up 2, haven't we? So it's still counting, it's just which direction do you count? So you lose factors when you use a negative. So I count out 4, back up 2, and I end up here. The answer would be x to the 4. Oh, it's still the rule. Add those numbers and get x squared, right? But notice that if I go this way, I multiply, which is addition up here in the exponent. And when I use negatives, I'm dividing. just the opposite operation, just like, so plus to minus, multiplication to division. So I can take any division and turn it into multiplication, or multiplication into a division if I want to, by changing the sign of the exponent. Like 1 over w to the fourth, it would be the same thing as, instead of dividing by 4 w's, make it a negative exponent, which means the same thing, to count backwards. So it gives you this basic relationship between an exponent and the same thing with a negative of the same exponent. If one divides, you move the other one so it multiplies. So either way, if I did w to the minus fourth and started there, I would say, oh, if I want to make that division, I just do 1 over w to the plus 4. Now, if you take something like w to the minus 4, w to the 4, and you do this rule, back up 4, go forward 4, where do you end up? So what does it mean to have 0 factors? Well, if I start over here, get some room. It means you're at 1, right? So with multiplication, the starting point of any process is 1, not 0. If you start at 0, you never get anywhere. Keep multiplying, you still get 0. So it's multiplication. It relates to multiplication, so the basic number for multiplication is 1. You start there, and then you build up factors. So a 0 power is always equivalent to a 1. So it's still just counting, but we have to start somewhere. So we start at 1 and then start throwing in factors, or dividing them out if you're negative. So now count. Count half of the factors of x. That's what that would say, wouldn't it? So, well, if I have half of them, and I throw in another half of them, where do I end up? The whole thing. That's what half of the factors should mean, that it would take half of those to make the whole thing. So if I put 2 of them, that should do it. Or if I took a third of the factors, then I should put 3 of those together. I get back to 1 of them, don't I? So fractions, 1 over in the exponent, we can make sense out of as counting, but think of it as, well, what part? How many of those? If it's half of them, I need 2 of them. If it's a third of them, I need 3 of them, and so forth. But there's another way to look at this. If 2 things multiply to give you the same thing, we usually call that what? Square root. So there's another notation for the same thing. That really represents half of x in terms of factors, doesn't it? If I took the square root of x twice, I get back to x. So they have to be the same thing. Which is true of this one, which is instead of the square root, it must be the cube root. So fractional exponents we can represent as radicals instead of exponentials. But if you think about it, it's still just counting factors. You need 3 of those to make the whole. So it must be the cube root. I guess if I want music, it's Muzak. Is that what they still call it? You used to call it Muzak. Or any other number. So 1/8 would be 8th root, and so forth. So now, the problem arises later, so you can get this all figured out right now, that these things come up, and you have the 1/over parts, right? So if you see 1/x squared, and you see x to the 1/2. There's a danger of mixing the two up. There's a 1/over something in there with a 2, right? So step back and think about that. This means you have 2 factors of x, but divided. This means you have half of the factors of x, doesn't it? Oh, so that wouldn't be division. So that's the... Okay. So probably this next week, not too much problem with that. 2 months from now, though, you think the 1/over, and you get the 2 mixed up, so be very careful. So think about what that would mean. How you're counting factors, so which one's which? It might help. So we can add and subtract exponents means multiply or divide powers. Right? There's another situation, something like if we had x cubed to the 4th. So a power of a power. So it would mean what? 4 factors of x cubed, but each of those 4 is 3 factors of x. So if you think about that counting, it would be 3 times 4, wouldn't it? So powers of powers become multiplications of exponents. Powers times powers become sums of exponents. So you have those basic exponential rules, which should probably seem a little familiar, right? More than once. But here it is again, but I tried to say it a little different. It's always, you can think about it as counting, even though they're fractions. You can think about it as counting the exponent, how many factors. So you have half of the factors, so it'll take 2, oh, that's square root. And rules like this, which we could formalize and put in more letters, should make sense. Right? So let's move to some problems. I wrote y to the minus 3. So, well, what are you going to do? Well, it depends on what else I say. But in this case, what would that be if I wasn't going to use negative exponents? Yeah. Oops. So divide by y cubed. Here I've written a fraction, right? 5 over p squared. Kind of. What would that be if I didn't want to use a fraction? Yeah. In both of those cases, there's really not a reason for one over the other, except in context. One might be more beneficial. So, I was checking something, did I? Okay. Trying to see, did I actually push that record button? Yes, I did. Which one, in both cases, which one is simplified? Well, they're both the same. It just depends. So I don't care if you use negative exponents or positive. That's fine, either one. I have a tendency to write answers without fractions. So I'd probably write this one and that one. Now, some things do require some simplification that we can make it much simpler, such as this situation where we have different powers with the same base. So you should be able to put those together. So if I have different powers of x, I should be able to combine them in the same way with the y. So I'll let you take a second, see what you come up with, and then I'll if you listen hard enough, we might be writing it on that other board. Click, click, click. Come up with, better check my own work carefully. Same thing or similar. Maybe not exactly the same way of writing it, but something equivalent. So I put everything except for the 3, the constant. I put everything into the numerator, right? Which is fine. And so I end up with 3 minus 4 as an exponent. The other one I better be careful. It's 2 minus a minus 7, isn't it? So it's going to be 2 plus 7. So it's another place that quick mistakes happen. It's when you get minus, minus. Somehow it ends up minus. No. So, and that's a perfectly good answer. I suppose I might even write it this way. Oops, not that way. If I didn't want fractions anywhere, right? So, so either of those fine. If you don't like negative numbers, well, you could also write it this way, right? So that's fine. And so writing it one of those 3 ways as a final answer, in most cases, well, doesn't make any difference, one of those. or maybe something, I don't know what else you come up with. The idea here is that what? The constant is simplified. We can't make it a simpler constant. The x is just one x factor, and the y is just one y factor with an exponent. Let's see. Go back and see where I numbered. Okay. Well, let's take one that puts together several things, maybe. Stand over here. So a little more in this one, but it's all a matter of rules. We want to go the same way. We want to end up with what? A factor, which is just the constant. A factor, which would just be x with a power. And some other factor that's going to be a y with a power. And there are different things we can do. We can combine x's, combine y's. We have this that would multiply the exponents inside. So you sort of have a choice of which things to do first. So if I took the inside part here, I could wait 3 minus 1 x squared I guess I'll do it this way. Subtract this minus 3 from this 2, and then it ends up dividing, doesn't it? So, but I could have worked with this minus 2 first, either way. Once I've done that, then I can distribute. This would be minus 2 factors of the 4, minus 2 factors of the x squared, minus 2 factors of y to the 5th. At that point, I might consider that 4 squared. I know what that is. So probably go ahead and write 1 over 16 since it's a negative exponent. The other part, it's sort of up to you, or what you might use this for at the next step if there was such a thing. But that's a perfectly good answer there, right? Oops. But here's another answer that would be equivalent, but if you like positive exponents, that'll work. And if I like, I could put another situation where there are no fractions, right? Again. So if you don't like fractions, you don't need them. So basic rules of exponents. Kind of a review. Think about it, it's just counting how many, but you can make sense out of that for negatives and fractions. Fractional exponents will refer to radicals. Negative exponents means what? Divide instead of multiply. Now, It said you don't have to use fractions. If in the past you were given this, one thing that you usually do with fractions is what? Reduce them, right? To lowest terms, usually said. So you find common factors, numerator, denominator, and then whatever the terminology is, cancel or take care of the ones. Leave it as a fraction, but I just as a illustration, we could write this without fractions and avoid them, right? Reducing at this point really follows the same thing. You would factor numbers. So, but now you can do it as products instead of divisions. As we would look at the fives, we have 5 times a 5 with a minus 1, right? And then I get a 3 times a 3 with a minus 1, another 3 with a minus 1, and a 2. But if I add exponents, what do I get? 0, 0, 3 to the minus 1 times 2. So I can do that just by using factoring the numbers and then multiplying instead of dividing. If at the end you like a fraction, well, I can make it 2/3. So with negative exponents, if you like to multiply and you don't like fractions, you can get by. And you might find that I do things a lot of times. I won't use fractions where in the past it seems like everybody told you to use a fraction. But this is simple. I probably think, oh yeah, I'd probably get the 2/3 quickly the old way, right, that you're taught. But where this might come in handy is if you have more complicated expressions instead of just basic numbers. So expressions made into fractions, you might like turning it into negative exponents and doing it this way. Okay. Now, making sense? You kind of remember the rules. I didn't formalize here those basic rules, you know, in terms of all the exponent n, m, but we went through them. You can read the more formalized version. Nothing to clear up right now. Okay. Always have to look. That's very small and hard to read from over here. We go to 3:15. 75-minute classes I have to get used to. At least they've gone to every class starts at a normal time instead of starting at weird. There for a while they did 75-minute classes on really weird schedules. I guess if you've only been here this year, you wouldn't know. Well, let's venture. Forward. And so I'll write down, not a very good penmanship, but factoring. And solving. So probably remember those, at least in some form, right? Had to go through and factor things, expressions, you had to solve equations. So in the past, you would have went and done a lot. Here's how you factor, right? Different techniques. And then later worry about, now we have equations solved. We're not going to take them apart that way. We're going to look at them together now. You know things about each. We're going to combine them and just take the parts we really need. So let's look at this basic equation. It's an equation. I have an equal sign, right? Between two expressions. X squared minus 4 equals 0. I say solve that. So what does that mean to solve that equation?
You're solving for X.
Yeah, you want X. Solving for X. Which X? What X? What is X? Yeah, it's the missing one. So if I say my solution is X is equal to 5, what would you say? I solved this, it's 5. You say, oh, you're the instructor, so you're right. What would you say? Well, I hope you say that's wrong. Why is it wrong?
When you plug it in, it doesn't equal 0.
Yeah, it makes a false statement, doesn't it? Because an equation is really an entire statement. It's a sentence in itself, isn't it? Which can be answered true or false, depending on the value of X. So that's what we get to solving. You're looking not just for X's in general, are you? You're looking for those specific X's, which if you substitute, makes that a true statement. That's solving. Of course, you know that, but it's been, now you just automatically kind of go by what that is. In this case, and we can come back to it, but minus 2 and 2 are certainly solutions, aren't they? Both of those make it true. Actually, there are no other numbers that do make it. It does do, anyway, make it true. Yeah, where did I start? Plural or singular, I don't know. So, and we have ways of finding that, but in this case, they're the solutions, right? And that's the whole idea. We get other equations. We want to know, when is it true? Because usually real world problems work that way. You set up a model equation, and so you want to know, when are these things true, right? So that's our solving. Now take the expression x squared minus 4, and I can say factor that. So, well, there are common factors, different thing, but usually that's reduce the powers that appear. And factors would be products. So again, I could write down equivalent product to that set of terms, right? Which is then factored. And you probably learned techniques or might have already written that down or thought of it quickly, right? Or maybe not. But you at least know what that's about. About the same thing there, isn't it? Really, if I do one, I've done the other. If I factor this, then I can find the solution, right? It's the opposite sign of that. If I find the solution, it also works the other way. It tells me the factors. So either way. Factoring is solving, solving is factoring in essence. They're not really separate things. So, but at some point back there, you had to learn them separately because you had to build the math first. Right? But now you know something about both of those. So we don't need to separate them. We can take advantage that this is the relationship. Factors give you solutions, solutions give you factors. Oh, well, before I get too far. I have to get used to, I cross my Z's. The word solution is also referred to as root of an equation or a zero of an equation. So we might interchange those words. So just to be aware. So root has to do with square roots, but there's also just any equation. Solutions are also called the roots, whether there's radicals or not. So now I'll be a little bit more abstract here to write this down. So we have a solution to an equation. So R solves the equation P of X equal to 0. P of X just represents this expression in the variable X. So that's the setting. So here's what we were looking at before in a more general, written out, slightly more abstract. That if you have a solution to an equation, then if you write the expression in the equation equal to 0, so you have to put it that setup, then you also have a factor. If you can factor out the thing from the expression, then you have a solution. Notice that the factor has the opposite sign of the solution, right? So if you need factors and you know a solution, yeah. If you need a solution, you might factor. So you might do it either way, depending on what you know and where you're going. So we'll take advantage of this because, well, first, what time is it? Need that corner, because from over here, that's a strange angle. Can't read it hard. So let's look at basic solving. When it comes to first degree equations, like 2x plus 5 equals 7 minus x. There we don't really need to consider factoring. That's our basic thing that you can solve fairly straightforward, isn't it? So work on that for 30 seconds and see what you come up with. What value of x makes that true? The first thing is first degree, so there's what? At most the one solution. And there's some standard basic technique for that, isn't it? So you would add or subtract exactly the same thing from both sides, still have an equivalent equation. And the other thing is to do that so that you end up with variables on one side, constants on the other. Sometimes said to be add equals to equals. You get equals. And the other thing you can do is divide or multiply both sides, right? And then you finish up. As long as you don't divide or multiply by 0. So, again, might have taken a little recall there, but I hope that's not a problem to solve a first degree equation. Oops. Second degree, so things which have squares, first degree, and constants. So you go through a lot of solving, working with quadratics, factoring, and solving this way and that. And then finally, you come upon quadratic formula. And you find, well, that's all you need. So you don't need anything else. But you need all the other stuff to build up to that. But once you have the quadratic formula, it says if you take a general quadratic equation, if you solve it in this, set it up in this form, quadratic equal to 0, coefficients a, b, and c, then the solutions come from the coefficient by what? Minus the b plus or minus square root b squared minus 4ac, all over 2a. At that point, that's all you need. You can solve every quadratic, there it is, right? So if you want to, you can get by just with this when it comes to solving quadratics. There are some quadratics that if you played with them can be simpler because you don't have to simplify that expression. So if I had 3x squared minus 2x minus 1 or something equal to 0, I can solve. Because I get negative the coefficient of x plus or minus. So this has built-in two solutions, one with the plus, one with the minus. B squared would be 4, this squared, so 4 minus 4. A is 3, and C is minus 1. All over 2 times the 3. So I've solved it. Now, it might be nice to write that in a more aesthetic form. 2 plus or minus, this is actually 4 plus, oh, I picked some nice numbers, it looks like. Plus 12, so 16. And so 2 plus or minus 4 over 6. So at that point, if I end up having a radical, I'd probably leave it in this form. In this case, I can come out with two nice rational numbers. So I get 2 plus 4 over 6 and 2 minus 4 over 6. Right? So a 1 and a minus 1/3, I think so. So it does it. So every quadratic you can solve with the quadratic formula. In this case, you might have gone back and done some other technique and done the same thing. But you wouldn't have to. That's the. On the other hand, let's see, what did I write? As long as it's not. Yeah. I had 3x squared. So minus 2x minus 1, right? Yeah. What are the factors of 3x squared minus 2x minus 1? Well, x minus was one of the roots plus 1. I can back up. Did I have the sign? Oops, I can't find my little. Yeah, plus 1 and minus 1/3. So the factors would be x minus those two solutions, except this isn't quite equal to this. We have to make an adjustment. These are factors except the leading coefficient, 3x squared. This is x squared, isn't it? So we'll have to do that. And if you don't like the 3 out here, notice if I bring the 3 into this one, that's the 1/3. I could have written it this way. So these are the factors, but I need to compensate for this leading coefficient if I do it that way. If you don't like this fractional form, you can put those together and write it without fractions. So now if we need to solve something, a lot of things will just quadratic formula or something. Or if we need factors, we might use the quadratic formula. Okay. Then we'll look between now and Tuesday. Right? Look at the website, the syllabus, read through that. Work on section 1 homework might be a good idea. See if there's anything there.